And so we'll start now. Uh, last time we discussed about the support vector machine, and we started implementing our application, right? So what we are going to do now is to simply go through the codes and identify what we are going to do in this practical, right? Okay, so I told you that this problem is a very, a straightforward question, but we have like do several techniques in order to get it done, right? The first thing is now we identified the features and labels. So you got to know the labels are quite straightforward, since the labels like we want to identify 3 persons here. Therefore, there will be 3 labels like Obama, right, Trump, and Bush, right? So those will be the labels. Understood? And uh, thereafter, what will happen is that uh, that we had to identify features. So you got to know that the features will be the face, just the face image, the pixels of the face, right? The pixels of the face. So those will be the features. So we got to know about that as well. Thereafter, what we did was, okay, we got to know about images, and we know that gray images and color images. So we got to know about these things. And then okay, so faces will be the features, and each label like 0 for Barack Obama, 1 for George W. Bush, sorry, Trump, and 2 for George W. Bush, right? So 3 labels are there. Now, the important thing is that here that we use use something called principal component analysis in order to reduce the number of features. Like we have 2D image 50 by 50, so 2,500 features altogether, and we convert it to a one-dimensional array, 1D, and thereafter we train it to the support vector machine, right? So this is called the pipeline. So the principal component analysis will be simply used to reduce the features, right? Reduce the features. Understood? Okay. So I think that's how we are going to simply do this, right? Got it? And this is called the pipeline. And the most important thing that the images that we had, they were like having background as well, but what we need is we need only the face. So therefore we need to have a method of segmenting or cropping the face and getting the face, right? So in order to do that, what we do is we use something called Haar cascade classifiers. And using Haar cascade classifiers, what we will do is simply we get this thing, and then the face detected, and thereafter we apply it to the algorithm, the pipeline, the support vector machine, and principal component analysis. Then we can get predictions, right? So that was the target yesterday in order to implement this, right? Okay, so what we do first is that we are going to load the data set and get the data set into our code, right? So here we use one important library available in Python called the OS library, operating system library. So the operating system library allows us to actually get, uh, in order to do things um, like using the operating system, like file operations and everything, right, could be done using this OS library. So very important library. And in the OS library, now here what I have given is the data path. So this is where my, can you remember now, this is my code, and this is where my training images are saved, right? The training images are saved. So this is my code. So what we'll do is I provide the training path here. So what happens then, in the OS library, we have, OS is an inbuilt library. Now don't think that we need to like use pip install and get this installed. No need to install the OS library separately. What you can do is simply, the OS library is an inbuilt library. That means it comes with the Python installation. No need to install it separately, right? So thereafter, what we do is, in the OS library, we have a method called list directory. And this list directory, simply what it does is, it can take a path given. It can be a relative path or absolute path. Once a path is given, what happens inside that path, whatever the files including the folders, everything, so it gets the file names, the folder names and everything into a array, right, into array. So you can see that I have printed the labels. So these are the labels that you are going to see. Understood? So what it does, simply it, I mean, read whatever the file names available in a given location, right? For example, if I do something like this for your, let me provide some other, right? Yeah. So this is some other path in my computer, right? This is some other path in my computer. So if you provide that path into this one, what happens? It reads all the file names available in that given location and take them into a array, a Python list, and it is printed here, right? Got it? Now you can see it clearly. What happens is that it's simply getting these folder names and file names into this label. So that's what happens simply. Understood? So no matter what's the path, whatever the folder names, file names inside the given path will be loaded here to a list. Now this is a list, a Python list, or in other words, we can refer it as an array. Got it? Understood? Right? So thereafter, what I do simply here, I mean, like we have two labels, therefore I'm using this np.arrange. So what this np.arrange simply says, okay, now np.arrange 0 to 10. So, oh no, np.arrange 10, let's say. So what it does, you can see it creates an array between like 0 to 10, 0 to 10, but not go up to 10, it go up to 1 minus 10, that means 9, 0 to 9, right? So similarly, now the length of labels, you can see that it is something like 3, right? So this creates a array called categories, a list called categories 0, 1 and 2, right? Now don't worry what's the usage of these things, but I will explain. Thereafter I create a dictionary, a Python dictionary combining these labels and these categories. So it will create a dictionary like this: Barack Obama 0, Donald Trump 1, George W. Bush 2, right? So likewise it will be created here. Understood? That's what we are doing in this one, right? So now you will get to know what about these things, right? I will let you know the full explanation, right? Got it? Yeah. So thereafter, what I'll do now, let me go step by step here. Uh, then I'll do something like this for labeling labels, right? For labeling labels, right? So if you print this, what you are going to see? Labeling labels. So that means it's going through each and every element in this array, right? Yeah, right. So it's going through the each and every element in this array, right? Understood? So thereafter, what we do, I'm going to get something like this: image paths, right? Image paths equal os.path.join data path and label. So what the os.path simply does, right? The os path simply does that it combines two given paths. Now the label, you know, the Barack Obama, Donald Trump, George W. Bush, but you know the data path is like train data too, right? So then you will understand what will be the image path. It's going to combine the train data and this one of these folder names, and it creates a path like this. Got it? Understood? So it simply creates a path, right? It simply creates a path. Then what I'm going to do, inside that each path, right? Now the image paths will be, okay, first time, now this loop iterates 3 times. Each time, the first time, I mean, this will be the tag, I mean the images path. Second time, this will be the images path. Third time, this will be the images path. So what we do simply, we pass it here, right? And again, inside now, you know os.list directory, what it does, right? So what we do, we pass this now and take the whatever the file names available in this path to this image names, right? So then you will probably understand what happens here. Let me print the image names here, and image path and image names. Then also I will print a separator in order to identify the like it separately, right? So this is what happens. Okay, now train data to Barack Obama. That means that image path 1 at the first iteration of the loop. Then the image names will be, see, all the image names available inside that folder, right? And now this is the separator. So this is the second path, train data Donald Trump, right? So these are the image names available in Donald Trump. Got it? Understood? So likewise, we are going to go through each and every folder and get the image names in each and every folder, right? So that's what we do here. Understood? Now, any questions you ask, please, right? Okay. So you know that what image names are, right? So then what I'm going to do, you know that this loop will run 3 times, right? This loop will run 3 times. And then what I'm going to do, that means going to go through each and every folder like Donald Trump, Barack Obama and everything. Then thereafter what I do, I'll do something like this. Image name in image names. Right? Image name in image names. So can you like guess what happens here quickly? Yes? Yes. So you can see that this will go through each and every image inside each and every folder, right? Isn't it? Yes. So let me mute you all. So if you have any issue, you can unmute and ask, right? Okay. So okay. Right. So what happens here, it will go through each and every image and read each and every image here and like the image name, right? Got it? So if I print the name, this loop will run through each and every image. Right? Got it? Understood? So each and every image name. Thereafter what I do, now this is only the name, right? Only the name, right? So you can see, okay, the name number 1, the name number 2, likewise, only the name. It prints only the name, right? Only a single name. Let me comment this out. Now this would be images name. Sorry, images name. Sorry, image names. This one, image names. So I'm going to go through each and every image name, right? See, got it? So this loop will go through each and every folder, and this loop will go through each and every image in each and every folder. Understood? Right? Okay. So is there any issue with the internet? I mean, the lagging or any kind of issue now? Is it okay now? It's still there. Okay, great. So you can see it goes through each and every image. Understood? Got it? So then what I'm going to do now, you can see only the image name is here, right? Only the image name is here, right? Only the image name. Got it? So what I'll do is quickly, I'm going to get the image path. So image path will be simply the os.path.join. I'm going to like the image path. Now I'm going to now carefully look at this. Now this is only having the image name, right? So when you print it, it prints only the image name. But here I'm going to combine the image name with the image path. And let me show you now the output image path, what this image path simply means, right? See, now it's like me, it's giving like the full path, right? Not the only the name, but now it gives the full path, right? Train data, Barack Obama, and the image name, the full path. So this image path will be the full path of the image, right? Understood? So thereafter, what I'm going to do, each and every image, I'm going to use the imread command available in the OpenCV module, and I'm going to give this image path. So this simply loads this image into our code, and it loads this kind of a object, right? So now this is where we really load the image into into a physical object in the Python, right? So this is where we load a real image, right? Right. So then let me show you that image, cv2.imshow. I'm going to open a window called live, and let me show you this image. And I'm going to provide in between each image, I'm going to provide the 100 millisecond delay. So that's what the wait key simply does. So we use the OpenCV library. So this is what the wait key does. It waits simply like this, and that's all. So that's all, and so we run this and see. Probably we have to import the OpenCV library. See, right? So it's load the each and every image. Right? Right. I think you understood, right? What happens? Now, actually, no need to visualize it. So thereafter, what I'm going to do now, the first thing I will do is I convert it to a gray color image. I simply convert it to a gray color image. Right. So you know this thing, right? So it converted into a gray color image, right? Thereafter, what we are going to do now, what's the purpose of using a gray color image? Now we are going to use something called Haar cascade classifier to segment the face. I think you can remember, right? I told you that we need to segment the image, so therefore that's why we convert it to gray, since the Haar cascade classifiers are only working with gray images. So we need to get the gray conversion here, right? So what I mean by gray is simply like this. Right? So if I show you both these things, got it, right? Right, got it. Okay, great. Now no need to show it here, but yeah, let us keep it. Now everything is done. Now what we have to do is we have to only detect the face, right? Detect the face. So in order to do that, we use something called a Haar cascade classifier, right? So that file is included in your code, Haar cascade frontal face default XCML. So this is the Haar cascade classifier file we are using in order to detect the face, right? So therefore we load it. Now I'll explain what it simply does by a Haar cascade classifier quickly. Give me a second, but I will first load the Har cascade classifier like this. So there is a function in OpenCV called cascade classifier. When we give the path of the cascade classifier, it loads it to this kind of object, right? So here we simply load the Har cascade classifier. Now let me quickly introduce you to the Har cascade classifier. Now, um, right. So this is what simply a Har cascade classifier simply does, right? The Har cascade classifier simply does. Um, okay, right. So now this is in the actually this is in the day 2 fold, right? So this is in the day 2 fold. You can get it from there. Right? Okay, right. So what as I mean, if you want to get this file, this is also in the this is also in the um, the day 5 day 6 folder. So this is in the day 6 folder, right? So this is there in the day 6 folder, so you can get it from there as well, right? Okay. Right. Okay. So what the Har cascade classifier simply does is now Har cascade classifier, one Har cascade classifier is there to detect only one object. So that means if it is a phase cascade classifier, it can detect only phases, right? If it is detecting bikes, it can only detect bikes, right? So likewise, a Har cascade classifier is designed to detect one object, only a one object. Got it? Right? So that thing is there. So therefore, like we are going to discuss about Har cascade classifiers in our last day, right? So in detail, we are going to discuss about Har cascade classifiers. So therefore, I'm not going to discuss it today in detail. But anyway, Har cascade classifier is simply designed to detect a single object, So we have lots of Har cascade classifiers. So we will get to know about bike detection, vehicle detection, right? So those kind of Har cascade classifiers in our last day of our lecture series. But today we are going to simply use the phase Har cascade classifier and detect a phase, right? So when a Har cascade classifier is there, what it simply does, we input a image to that Har cascade classifier. So what it simply does is that it detects if there is the interested object is there. That means now if you do if you use a phase cascade classifier, so when you provide the image with the phase, what it does is it detects the phase like this, and it provides us this x, y, wh parameters, right? It simply provides us x, y, wh parameters. That's what it simply does, right? Now don't worry about this, since I'm going to discuss about these things in detail in the last day, but not today, right? I'll discuss about these things in detail in the last day, but not today. So therefore, I hope that this is enough for today, right? So when Har cascade classifier, we can have like Har cascade classifiers to detect any object, right? When we have a phase cascade classifier, a single Har cascade classifier detects only one object. So if it is a phase, it can only detect phases, right? So now what we have is a Har cascade classifier which can detect phases. But we have other Har cascade classifiers as well to detect vehicles, to detect bikes, to detect eyes, to detect number plates. Likewise, we have lots of Har cascade classifiers. But the Har cascade classifier that we are going to use is cascade classifier, the Haar cascade classifier for faces. Now, where to get these Haar cascade classifiers? Where to find more Haar cascade classifiers? I will explain about those things in the last day, right? So today we have the face detecting cascade classifier. What it simply does is when you provide the image with the face, it detects the XYWH parameters and provide us this bounding rectangle, right? So that's what the Haar cascade classifier simply does. But there's one important thing. Now, this is how we are going to use it, right? This is the cascade classifier that we are using. So what we do is we simply pass the gray image to this face classifier, right? We pass the gray image into this face classifier. And what do you mean by these faces is a bit different to what I just told you now. I want to explain that here as well. So let me quickly explain now. Assume that there are two faces in a single image, right? If there is two faces in a single image, what happens? Right? So what this simply does is it detects both. It can detect both. That is powerful, and it can detect both. It can detect both, right? So after detecting both, now you can see that these two have their own x1, y1, w1, and h1, right? And here also, this has a separate x that let me do it like x2 and y2, and this is, let's say, the w2, and this is, let's say, the h2. Got it? So phases would be something like this. I mean, the result coming here is something like this. Let's assume that there are two faces in the image. So it gives you like this: x1, y1, w1, h1. This is the column, a single row. This is a single row, and this is a second row. Right? Okay. So that means the number of rows are dependent on what? Quickly. The number of rows of this array. So this is a two-dimensional array, you can see. So number of rows are detected on what? In this faces array, it's a two-dimensional array. So you can see the number of faces, the number of rows in this faces array will be dependent on what? Yes, we have answers. Good. Let's see. Exactly. The number of faces available in the image, right? So each face is represented by a row. Number of faces available, like it will be simply the number of rows in this faces array. So the number of columns are simply 4. It will be a fixed value for x, y, w, x, y, w, and h. Right? X, y, w, and h. Got it? X, y, w, and h. Right? So those will be the phases. Right? So thereafter, what we do simply is that we go in each and every image, right? And we get the x, y, w, and h in each and every phase, right? So then what I'll do, let me show you. I'll draw a rectangle. I'll draw a rectangle in order to you to understand, right? So in OpenCV, this is how we are going to draw rectangles, right? In OpenCV, this is how we are going to draw rectangles. So you will pass the image where you want to draw a rectangle, and then you have, like, in order to draw a rectangle in OpenCV, you have to provide these parameters. What? P1, P2, right? These 2 points, right? So x1, xy of this one and xy of this one, right? So these 2 points. Now, therefore, can someone guess me? If you want, like, draw a rectangle, rectangle bound in these faces, you have to provide this point and this point, right? So okay, this point will be simply what? X and y. And can you provide me this point, the coordinates of this point? From, I mean, using in terms of x, y, w, and h, this point would be what? Yes, very good. X plus w, y plus h, right? So that's what we are doing here, right? So the P1 and then the P2 and then also the color of the image, sorry, the color of the rectangle. So the color of the rectangle here is given in BGR format, BGR. So it's a yellow color one. And this is simply the last parameter is the line thickness in pixels of the rectangle, right? The line thickness of the the rectangle in pixels. So here we are using 2 pixels width for the line of the, right? Got it? Okay, so let us then quickly run this and let me show you the output. Right, so you can see the faces are detected clearly. But yeah, let me slow this a bit. Let me run it with 1000. That means 1 second delay. It detects it fine. But can you see some false positives are also detected, right? Can you see? Right? Some false positives are also detected. Unwanted objects are also detected. Right? So then what happens if you train the algorithm with using this tie, right? Likewise, if you use the background and train it, what will happen? Huh? What will happen, right? So the accuracy will get low, right? I mean, without faces, you are going to provide some background faces and say that this is Barack Obama, right? So you are going to provide some background faces and say this is Barack Obama. It's not going to work, right? So your accuracy will drop down. Yes. So what we need is now, yeah, we need to crop this now, right? We need to crop each and every, I mean, so you can see some unwanted things are also detected now. This is something usual when it comes to object detection. Always some false positives are detected, especially with this cascade classifier. Since this cascade classifier is a very old technology, something came in 2002 and 2000. So very old technology, but these are built up somewhere around 2008, 2006, but still it detects always some false positives. Therefore, what we have to do, we have to get rid of those false positives, right? Therefore, we are like actively involved in this data set creation, right? So we have like supervised this data set creation, right? So what we'll do here is simply I'll first crop the face, right? So now how to crop the face? Now let's say, so you have a face detected here, right? And you know that it simply gives you these parameters, right? So you know that it gives you x, y, and w and h. So what I'm going to do, I'm going to like crop it, right? See, very simple. What I use, cropped face, right? From the gray image, from y to y plus h, and from x to x plus w, I'm going to crop it and take it to a new thing, right? So if you are wondering what this crop face is, let me show you. Right? So this is the crop face. See, sometimes unwanted things are also detected, right? See, this is the crop face. Yeah. Now we have a question, why crop start with y? Now can you remember? I discussed this in the first day as well, right? So image is a two-dimensional array, right? Two-dimensional array. So y is the rows, right? Y is the rows and columns. Now can you remember indexing? I told you like first you have to give the rows, then you have to give columns, right? Understood. So first rows and columns. So you can see y is in the rows. Got it, right? So we have cropped the face now. Now what we need to do is we need like how we need to get involved here. And each and every cropped face we have to inspect and accept it, right? So what I'm going to do, right? I'm going to like, okay, wait the infinite time here, right? I'm going to wait an infinite time. So what 0 means now, earlier we used like 1000. So what 1000 simply does, that it waits for 100 milliseconds. But if you put 0, that means simply wait infinite, wait forever, right? Wait forever. Then what we do is I'll show the image here. Right? The crop face will be shown, and I wait here. And let me ask a question like this. So I ask a question. If you want to accept this cropped face, press Y or else N. Right? So it's asking us a question, right? Whether you want to accept this image or not, the cropped face or not, right? So the wait key simply, now there's the important thing about this wait key. Wait key is a function available in OpenCV. Now this is the delay or the delay that you need to wait in milliseconds. But what happens when you provide 0 simply, it waits infinite time, right? But until a key is being pressed, right? Until a key is pressed. That's what you mean wait key. So it waits infinite many times until a key is pressed, right? So in that time, if a key is pressed, whatever the key is pressed will be taken into this K, right? Whatever the key that you are going to press will be taken into this K, right? And we can check whether this pressed key is a Y, right? How we are going to check it? I'm going to check whether K is 1 to 1. Okay, so why I use like 1 to 1? Can anyone guess? 1 to 1 is simply Y. I mean, Y in the sense the character Y. Yes, exactly. Very good. It's the ASCII value. Let me go to the ASCII table quickly. One to one, Y. See, 1 to 1 is Y. Got it? Got it? Understood? So what we simply do, we crop the face. Sorry. Sorry. Yeah. This one, not this one. Yeah. We crop the face, right? We crop the face and we show it to the user, and we wait infinite many times, infinite time until a key is pressed. Once a key is pressed, see 0 means like infinite, wait infinite time. Once the key is pressed, it takes the key into this K, right? And we check, okay, whether that key is 1 to 1, that means whether that key is Y, right? Okay, so if that is Y, what we are going to do, then that means it should be accepted, right? It should be accepted. Therefore, what I'll do, I'll create something called data and target. Data and target. So what I'll do here, I'll simply append the I have like resize it to a common size now. These cannot be in the same size. I mean different sizes. So we have to resize. You know the resize command. We used the resize command earlier. So we convert it to a common size like 50 by 50, and then we append it to the data, array called data, and to the target what you have to append. So data and target, you know it from the standard definition, right? So we append the feature, the set of pixels of the face. That's what you call the features, right? Set of pixels of the face to the data, and we append target to the target what we have to append. Huh? Yes, very good. We are getting answers. The label, exactly, right? So the label. So how we are going to get the label? Label in the sense like we have to give like 0, 1, and 2, right? 0, 1, or 2. You have to get 0, 1, or 2. Yeah. So you can now you can keep a track about the folder that you are currently reading these images from, right? You can keep a track of the the folder that you are currently reading images from. Now this is going from like each and every image separately. I mean each and every folder separately. First Barack Obama, then to the George W. Bush folder, then to the uh, Donald Trump folder, right? So what you are going to do? We have the label, that means whether Barack Obama, Donald Trump, or George W. Bush. So what we use is we use simply this category dictionary, right? So what happens is we append the category dictionary label. So what happens here, you know the label is either Donald Trump, Barack Obama, or George W. Bush, right? So let's say George W. Bush. So then the category dictionary George W. Bush, that means what? 2. If category dictionary Donald Trump, that means 1, right? So what happens is that we append that into the target. We append that into the target. So to the target, whether sorry, into the target we append like 0, 1, or 2 with the image, right? So that's what we do here. Now what we have to do is simply you have to run this. Yeah, I did a small mistake here. Now you have to ask the question here before waiting. Yeah, there's a question. We need to convert it to 1D. Yes, we have to convert it, but I'm not going to do it here, right? So I will do it in a separate place. Yeah, so you can see now it asks if you accept this crop face, press Y, right? So that means it shows us this one. Sorry. Yeah. Right. So then we ask like, okay, to accept this, yes. This, no. So then press another key. No matter what the key you are going to press, it's fine, right? Since it only checks for Y. If it is Y, then only it takes. Like you can now this is you are going to accept. This is not, right? So now you have to spend a lot of time here and get it done, right? Get it done anyway. So that's the method you have like involved in like filtering out these unwanted images, right? So you can do it and the images and the targets will be appended. So finally what we do simply here is that we convert the Python list, the images set into data, and we reshape it to 1D, right? We reshape it to 1D. Now I will explain. Uh, let me, yeah. Okay, so I will explain what happens here, right? Right, so what this simply does is this convert it to an numpy array and then it reshape to 1D. That means what? Whatever the image set you have, like 50/50, that means 2500. And thereafter we save this data and target arrays into two physical files, data and target, right? So we save it to two physical files. That's what we do here. That's what we do here, right? So this is for the reshaping, right? Now let's assume I can't show you without running the whole image, right? So the data shape, like after doing this, the data shape simply will be something like this. Okay, like let's say three, it will be something like this. Okay, 360, 50, 50. I mean the data shape. So what it mean by the data shape? What do you mean by this? 350, 50. For example, it will be something like this, similar to this. I'm asking what I mean by this. Yes, any idea? For example, after you running this, it will simply become 360, 50 by 50. I mean 50, 50. What this means? After running this, no idea. Yes, exactly, right? So can you remember that 1797 50 50? I explained it yesterday or the before yesterday, right? So this is 360 50 by 50. That means 360 images with size 50 by 50, right? So now this is data shape. This is shape 0 and this is shape 1. This is shape 2. This is an array, right? This is an array. So this is shape 0, this is shape 1, this is shape 2. This is not an array, this is a tuple, right? So what do you do? Here 360 comma 50 into 50. So what's the size we are getting here? Well, we did it yesterday as well, right? Yes, 360, 2500. Right? So we are flattening it. That's what we are doing here. Flattening. We flatten the image here, right? Then finally we save it to physical files, data and target. So data and target will be available here. Data and target will be available here, and these are numpy files, right? NPY files, numpy files. So if you open this, you can't see anything. These are encoded. These are kind of encoded files. Anyway, those are numpy arrays, physical files of numpy arrays, but you can't read it using any other software, right? The only method of reading it is simply getting it to another file. So here what we do, uh, we load that data and target here, and let me show you what this simply means. Right. So what this simply means, 2800, I mean 285, 2500, right? So we have like 285 images with 2500 features, and targets what? Targets corresponds what? Targets corresponds the labels of each and every image here, right? Got it? Right. Okay. So here what we do, now we have the data and target loaded here. The features and labels are okay. Now the thing is, I skipped this, right? I skipped doing this, but I mean, you have the data and target with you, so no need to do it, but just get the idea that this is the way to do it. We have to go through an each and every image and crop it manually, otherwise the accuracy will be quite low, right? So then what we will do is we get the support vector machine with the RBF kernel as yesterday, as I mentioned, RBF kernel. And the principal component analysis, I will actually discuss about this under unsupervised machine learning, not today, but we get the principal component analysis and we make the pipeline. So what I mean by the pipeline? See, this is the pipeline. The principal component analysis, which converts the 2500 into 150. There's a reason in order to get 150. I will explain it later. Unsupervised learning and unsupervised learning, but then we get the support vector machine trained here. Right. So this is that pipeline I was talking about. You have the principal component analysis and the SVM. So two algorithms, combine those together, make sure the order matters, PCA then SVC, right? Then what we'll do is we then get the data set splitted, the data and target splitted to train data and test data, right? So you know what happens there. We discuss about these things, right? Then what we'll do, we train using the train data and train target. We train it using the train data and train target, and we use it for using the train data and test target. So when you predict, like we are getting almost 90% accuracy, that means a good model, right? And we will run this one as well, so you can see the accuracy, the precision of each and every one, right? The precision of each and every one. So Barack Obama, like there are 11 training data. Don't, I mean, you know that there will be altogether how many? 10% from the 1 to 285. So 285 is the 85 is the whole number of data. So from there we get 10%, 10% of it. So 10%, and what we'll do is simply that will be like somewhere 28, right? So 28, 11 is 29, let's say. 11 is Barack Obama, 10 is Donald Trump, 8 is George W. Bush. That means this is the distribution of the testing data, right? From the test data, from the test image, we have 11 Barack Obama photos, 10 Barack Obama Donald Trump photos, and 8 George W. Bush. And this is their individual accuracies, I mean precisions, right? Okay. So yeah. So then finally what we are going to do here is we um, train it using the support vector machine, right? We train it using the support vector machine. Sorry, we have trained it, so we now save the model into a physical file, svm face recognition.sav, right? Support vector machine face recognition.sav, right? Done, right? So thereafter what you can do, testing the model. So this is the code that you are having. Right. So first what we do is we load each and every image. Before loading the each and every image, we load the support vector machine model that we just saved the code, the earlier code. We saved it here. So what we'll do here is that we load that model here. And then we have the category dictionary. Now, can you see the category dictionary is the inverse of the category dictionary available earlier. Now, if I show you the category dictionary available earlier is something like this. Barack Obama 0, Donald Trump 1, George W. Bush 2. This is the dictionary we had earlier, right? But now, this is what we have. This is what we have like the other way. 0 Barack Obama, 1 Donald Trump, 2 George W. Bush. Now, this dictionary is quite useful. I will explain why later. But now we load the model and we have some test data in this test data folder. Some Barack Obama images, some George W. Bush images. Likewise, we have some sample images to be tested here, right? So what we'll do is we get the OS and CV2 library, and we have the test path, the test data path as test data, and we load, as earlier case, we load the face classifier. And what we do in the test path image, we get all the test images names here, all the test images name. Then what we will do, we create the path, the test images path, and test image names, we get all the images names, and this loop simply iterates through each and every image in the test image folder. Obvious, right? Now you know this is the test images path, test data. So there are all the test image names will be taken here. And what we do here, we iterate through each and every image name, and we get the image path by combining this data path with this image name. So we combine the image name and the image path, and we get the image path of each and every image. Then using the OpenCV, as earlier, we load each and every image. Then we convert it to gray. Then we detect the faces there. And in each faces, what we are going to do, we draw a rectangle and we crop the face as we did earlier, and we the same thing, right? So we convert it to 50 by 50, and we thereafter we flatten it 1 comma 50 by 50, that means 1 comma 2500. Then finally it will be we have a question, let's see. Yes, so there's a question, why we always use a flattened image? Yes, the machine learning algorithms, most of them cannot work with two-dimensional arrays, so they are only working with 1D arrays, one-dimensional feature set, one-dimensional data. So you have to convert it to 1D. But neural networks, like some machine learning algorithms are there which can work with 2D, but most of the common machine learning algorithms, they can't work with 2D arrays by default. But neural networks, if you take, neural networks can deal with two-dimensional arrays, but always we have to convert it to 1D when you are dealing with machine learning, right? So we then crop the face and we apply to the machine learning algorithm, and machine learning algorithm gives us a result. Can someone tell me what this result is? What this result? What are the possibilities for this result, this prediction? Yes, others quickly. Not names. We trained this thing like 0, 1, 2, right? Yeah, exactly 0, 1, 2. So this gives you 0, 1, 2. But we can't show they are like 0, 1, 2. We have to then get the name, right? So that's why we use the category dictionary like this. So 0, Barack Obama. When it's 1, it gives Donald Trump. When it's 2, it gives George W. Bush. So what we'll do simply is we get the result and we pass it to the category dictionary, and the category dictionary get us the name. So then we, using the put text command, in the test image we put this name, right? And this is the simply like what we have to provide here is simply the images, the xy coordinate of this text, right? So we are like having the George W. Bush, let's say, the text, let's say Obama, right? So here now you have to plot this somewhere here, right? So this y and x should be provided here. See, now what we do is we cropped it and xywh. So xywh simply is about this one and w and h. So these are the xywh of the face detected, right? So what we do is like the same x, but y is like 10 10 pixel uh, up, right? Understood. So we like 10 pixels above the rectangle we show Obama, right? So that's what we have done here, and this is the font that we are using, right? The font we are using Hershey, I mean CV2.font Hershey simplex. The font, so the first parameter is the image where the text should be placed. Then what's the text? Now text is like Barack Obama, Donald Trump, or George W. Bush, right? Then this is the location where the name should be placed. So we place it like x, y minus 10, that means above from this rectangle. And this is the font that we are using, font Hershey simplex. So you can search about like OpenCV supported fonts. OpenCV supported fonts, right? See, font Hershey simplex, font Hershey plain, font Hershey script complex, right? So we use this one, font Hershey script simplex. Sorry, font Hershey simplex. This is what we use. These are the font types available in OpenCV. So you can simply search about the fonts OpenCV supported fonts likewise. So what happened? We use the fonts. This is the font that we are going to use here, and this is the font scale. Now, what we mean by the font scale is simply like the default font size will be 1. 1 is the default font size. So if you put 1 here, that will be the default font size. 1.5 means 1.5 larger than 1, the default size, right? So if you put like 0.25, 0.25, let's say, that means 0.25 is scaled down, right? 2 means if you put 2 here, twice the default size 1, right? And this is the, like, it's not like font size, not 12, 14, 16, no. 1 will be the default font size. 1.5 means 1.5 larger than that. Got it? So you have to provide the font scale, not the font size, the font scale. 1 will be the default, and you can give a scalar value and it will be multiplied with that and will give you the font size. This is the font color. So we use the green color, and this is the thickness of a font. That's it. So if you run this one, we have to load it. Got it. Understood. Right. Okay. So I hope that you got the idea, right? I hope you got the idea, right? Simply that's what happens. Now, what I want from you now, no use of identifying George W. Bush, Barack Obama, and these things, right? So what you have to do now is simple, right? Now, can you see? Now, the code that we have written, right? For example, let me show you. Yeah, Ravi, shall we have a look at your error at the end of the class? You can show me the error, so I will clarify it for you, right? Okay, right. So let me show you an example, right? Now the code that we have written up to now, it's a dynamic code. What I mean by dynamic, Okay, let's say that I want to add another folder here, let's say, right? And let me like Joe Biden, right? Joe Biden, and let's say I'm going to add some images of him here, right? Now, what happens if you run this one? See, it automatically get the modification, right? No need to do anything manually in this code. That's the power. I mean, that's the like the usefulness of this code, right? It's a dynamic code. No matter what the change that you are going to do the data set, it's just automatically, right? So whatever the thing, like then it will go through the 4 folders and read it and do whatever the thing that you need, right? So what I'm expecting from you is to do this for your family members. Let's say you have 4 or 3 in your family. Take some samples photos and crop it manually using the creating the dataset code, right? Crop them manually, right? Crop them manually, and what you have to do then? Test it for them as well, right? So very simple, right? So I want you to do it to that, right? Okay, so another thing that here, if you want to like test it for a video, these are the things that you have to change. Now here, if you want like test it for a video, right? If you want to test it for a video, these codes should be changed. You have to have a video source, like source equals cv2 dot video capture. And if you want to use the webcam of your computer or your PC, you have to put 0 here, right? Right? 0 for 0 for your webcam. And then like you can provide the, I mean, if you are using a video, then you have to provide the path of that video file. Right? You have to provide the path of that video file. Likewise, right? So you can provide this path here. I mean, this example, right? So if you provide like this, then it loads it from your file. I mean, a video file. 0, if you put 0, that means it's your webcam, default webcam. Now, if you have multiple USB cameras attached into your camera, then the default webcam always will be 0, and the second USB camera will be like 1. And if you have 2 USB cameras, 1 and 2, the other will become 2. Then you can access it. Whereas if you are using a video file, you have to just give the path file. I mean the path of the video file, path of the video file. Then what you have to do is you have to run an infinite loop while true. Then what you are going to do is simply infinite loop, and this is how you loaded the image earlier, but now you have to load it like this: red image. Then you can load it from the source.read. This is how we are going to read continuous frame from the video. Here, I think you have to wait a little bit, I mean, little less, 10 milliseconds. Otherwise, it will be like the frames will be changed with every 1000 milliseconds. That means 1 second, right? So you have to load your video source, right? Thereafter, what happens? Get it read, each frame will be read from here and do the same thing, right? Now don't worry about this video loading and everything. We are going to discuss about at the last day, right? So don't worry, right? So we discuss about that in the last day. Don't worry, right? I mean, I just wanted to show you, like, if you want to check it with the live video, this is how we are going to do that. We have to initialize the source, and change it to a while loop, and without loading it from the physical image file, this is how we are going to read the video frame from a video. It can be a video file or it can be a camera, right? Anyway, now this video loading and everything, we will discuss it under the object detection on the last day, right? Object detection on the last day, so we will discuss about that. Don't worry, right? Okay. Got it? So I expect from you, please try to do this to your own data set. So very interesting thing, right? So you can then like develop a door locking system, right? So one of your family members shows up, so you can unlock the door, or if you can send a message, you can have a camera attached in the door, then you can send a message when a family member is detected. Likewise, you can do lots of things, right? Using this one, I mean, if the face recognition can be done. So I expect from you to like simply do this to your family members using your own data set. What you have to do is simply here, just change the file names, folder names, and include your own data set. That's all. Understood? Got it? Right. Good. So now what we are going to do is we are going to quickly move on to the next topic of our workshop, right? So if you have any questions before that, you can ask related to this one. If you have any doubt, you can ask them now. Yes, no, any questions? Everything is fine. Okay, so seems no any issues are there. So we will move to the next topic, right? So today now the next topic we are going to discuss is regression, right? Regression. So you know regression problems. I discussed about these things in our first day explanation, right? So regression is simply about the approximating. I mean, simply this is about when your label, right? When your label is simply a number, right? Kind of real value, right? So rainfall in millimeters, the price of stock tomorrow, right? The kind of a thing, risk of having a heart disease, right? A real value or a number of continuous data, continuous value, a continuous target. If you are going to deal with a continuous target problem, a label which has a kind of what you call continuous number, right? Then that's called a regression problem simply, right? That's called a regression problem. So we will quickly move on to linear regression and get to know what this linear regression simply gives, right? So linear regression is always talking about best fit line. So this is called the best fit line optimization, right? Best fit line optimization. So let me show you what I'm trying to explain here, right? Um, um, give me a second to check whether this. All right. So yeah. So this is about, I mean, simply about, as I mentioned, uh, number. So if your prediction is a number, then it simply becomes a regression problem, right? So so we have lots of regression algorithms: linear regression, polynomial regression, support regression, decision tree regression. Likewise, we have logistic regression. We have lots of algorithms available under regression. But what we are going to discuss about today, I mean, what we are going to discuss today is about linear regression, right? So simply, uh, yeah, let me quickly check the file that you got, file that I have provided to you. I think I think this is the file that you got, right? Is this is this the file you are? It's with you. Okay. 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 Great. Right. Fine. So we'll go with this, right? So now, as I mentioned, it's always about best fit line, right? So example now, before going on to anything, let me show you an example. Now your data set contains something called weight versus height CSV, right? Weight versus height CSV. So it is something, I mean, some data related to uh, weights and heights of humans, right? So the first column is containing the weights in kilograms. The second column is simply about the height in centimeters, right? I'll quickly explain what I'm trying to do, right? What I'm trying to do. So the first column is the weight of a particular person in kilograms, and the second is about the uh, the height in centimeters of a person, right? So one row simply represent a person, right? Okay. So what I wanted to show you that um, actually I uh, want to remove a value from here. Unfortunately, I have included it anyway. Um, let me show you the file. Sorry. Can you please open your CSV file? Right? Can you please open your CSV file and remove remove this one, the last column, I mean the last row, right? Simply remove the last row of the CSV file. Weight was height, right? Weight was height. Please remove the the last file of it, right? The last file of it. Got it? Okay. So now let me save it back and close it and save it. I just removed the last entry, the last row. That's what I did, right? Thereafter, what I'm going to do here, let me run it again. So I use the CSV file. So this is something that we did in the first day as well, right? And thereafter, what I'm going to do, okay. So this is the distribution that we are going to have, right? This is the distribution that we are going to have. Got it? So, right? So what happens now? Assume that this is a, a problem with one feature and one label, right? A single feature and a single label. So feature, let's say the weight, and the height, let's assume as the label. Got it? So let's think this is a data set, and the weight, let's take it as a feature. So one feature, and the label, the label will be the height, the second column. Got it? Now these are not two features. Feature is the weight, label is the height. Got it? So let's assume that this is that kind of a problem. So then let's say that we want to train an algorithm which can train on the weights and heights, right? So simply that means once the weight is given, it should predict the height. That's what we do, right? Feature and the label. So once the feature is given, the label should be predicted. So that means now this kind of relationship, let's say, now what the linear regression algorithm simply does, right? What it does simply, it now I'm going to assume that, okay, the feature as X, right, and the label as Y. So we are going to provide set of X and Y values, right? So we are going to provide set of X and Y values here, right? Set of X and Y values. And what happens, the machine learning algorithm, the linear regression algorithm now trains for these set of X and Y values. So for example, we are going to take, let's say, 100 people, and each and every one of them, we take their height and width. We take their height and width, right? And we arrange it in a data set, and we provide it to the linear regression algorithm, let's say. So what the linear regression algorithm simply does, right? When you provide this X and Y, it now, the regression algorithms are simply doing this thing. Y equal fx, what we is discussed in the first day as well, right? Y equal fx. And today in linear regression, y will be something like this. Or we can simply say it like y equal mx plus c. It provides us a relationship mx plus c, right? Got it? So then what happens when unknown data is given, how the predictions can be taken simply. How the predictions can be taken simply, let me sorry. Right. How the predictions can be taken, then y bar will be simply f x bar. That means what? Y bar will be simply what? M x bar plus c. Right? Okay, so we have questions. Let's see what is your. Yes, right. So now, what do you mean by y equal mx? What do you mean by y equal mx? Yes, it's a straight line equation, right? No, not exactly passing through origin. if it is passing through origin, C should be 0, right? C should be 0, right? So when there is C, yeah, y equal mx plus c, it's a equation of line, right? So that means what the linear regression provides you, something like this. Right? It provides you something like this. Right? Y equal mx plus c, right? Okay. Now my question, how many lines that you can draw in this? I mean, linear regression provides you a line like y equal mx plus c. But my question, how many lines you can draw in this space, this x and y space? How many straight lines you can provide? I mean, you can draw in this space. You can again, like earlier, yesterday's case, yes, we can draw infinite many lines here. Not only one, we can draw infinite many lines. Okay. We can draw infinite many lines here, number of lines, right? A number of lines. So what happens then? Right? What happens then? But we need only one line, right? We need not a one line, but we need the best line. That means the best fit line. So how many best fit lines can be there in this for this data set? I mean, yeah, for this data set, how many best fit lines can be there? Yes, I mean, a silly question, right? Best. There will be always one best, right? Only one best. Got it? So the machine learning algorithm then provides you a equation, right? Like y equal mx, not exactly y equal mx, but it provides you something like this. Y equal mb x plus cb. It provides you the m and c of a equation, right? So let's say now you have data to be predicted, x bar. Now a weight of a human is given, right? So what happens? How we are going to provide this? Right? So if you know the mb plus c, you can find the y bar, right? Obvious, right? So you know, if you know the y and m and c, you can find the y, right? For example, let's say x is 85. So if you know, like if you know m, like let's say mb is 2 and this is 85 and let's say cb is 5, right? So this will be the thing, right? That means y will be something like this, for example. Got it? I mean, I take m and b, mb and c like just some random values, right? They are not exact values, right? This is where y bar is, right? So now, right? Yeah, m is the slope, right? mb is the slope. Now, my question. Uh, yeah. So my question is simply now. There will be one best fit line, right? So can you like provide me how this best fit line should be taken? The objective behind the fit line in order to obtain the best fit line? Yes, exactly. The least squared method, right? That means what you are going to do simply, right? Sorry, right? So we are going to measure these distances. So these are called the errors. We are going to measure the distance from this line to line, these points, right? And what we are going to do is, these are called the errors. Right? So we are going to sum these errors, right? Sum these errors, right? So then this SE, when the summation of errors, SE is simply these errors. The difference between the y difference between the line and the this thing, right? So now let's say this is a equation like y equal mx plus c. So when SE becomes minimum, right? When SE becomes minimum, right? M becomes MB and C becomes CB. That means if you have a line like this y equal mx plus c, right? If you can find a line which has the minimum summation of errors, right? Which has the minimum summation of errors. So if you can draw a line with the minimum summation of errors, the M and C will be the best fit lines M and C. Got it? Right? So M and C will become the best fit line. Yes, right? So that's like the best fit line. How you can define the best fit line? When you draw a line to this, if that line gives you the minimum summation of error, right? That line is the best fit line. That means that M and C are the best fit lines coefficients, right? So you can derive this, right? So you can derive this without any doubt. You can derive this, but I'm not going to derive it now. But anyway, by deriving, I think uh, yeah, the proof is there. I think you have this link. So if you want to see how this is actually done, how this M and C is calculated, you can go to this link and find out how this is actually calculated, right? So this, I mean, step by step, it explains how this is done, right? Got it? So that's how anyway it's done. Okay. So anyway, the M and C will be these things, right? M and C will be these things. So how we are going to calculate M and C of a best fit line? Now B is actually C, right? This B is C. This should be C, right? So M will be x bar into y bar into xy bar into x square bar, I mean x bar square minus x squared bar. So what we mean? Huh? So let's say that you have some x values and let's say that you have some y values, and x1, x2, sorry. Height and width, let's say, right? x1, x2, x3, x4, x5, and let's say you have up to xn. So x bar is what? You are going to add all of these x's 1 to n xi and divide by n. So that's what you call x bar. And y bar is similarly the y values, right? So y bar is simply the summation of all y values and calculate the average or the mean value, right? Calculate the mean value. Yes, mean value, the average, right? So then what we mean by xy bar? You are going to get the xy. That means like this. Right? So you are going to get like x1, y1, x2, y2, x3, y3, and xn, yn, right? So then xy bar becomes sigma I equals 1 to n xi yi divided by n, right? So we are going to get the xy multiplication and get the addition and get the mean of xy thing, right? And similarly, what would be x squared bar, right? So this will be x squared bar. X1 squared, x2 squared, x3 squared, and finally xn squared, right? So x square bar will be simply the summation of all xi square values and get the mean, right? So then what do you mean by this one? That's nothing but x this will be simply x bar square, right? X bar square. But two things, right? X square bar and x bar square are two different things, right? Got it? So, but anyway, that's how we are going to calculate the m, right? That's how we are going to calculate the m. And I think you got the idea, right? That's how we are going to calculate the m. And simply, if you can, yeah, we have a question, let's see. Yeah. Then if you can find m and how to find c, y bar minus that found m, this m, into m x bar. That's how we are going to find c. Right? Got it? That's how we are going to find c. Okay. So now everything that we have discussed up to now, right, is something only works with what? Works with what? When you have only one feature, right? When you have only one feature. So, I mean, yes, like height and width. So everything works like linear equation works only with y equal mx plus c, right? Only one feature, x, only one x, right? So then you will be wondering about, okay, what happens when you have multiple data? For example, this is what we are going to do today. The cardio data set. This is something that I found on Kaggle, I think. I can't exactly remember. I will probably provide you the source, right? Anyway, this is a data set. So one row represents a patient, right? One row represents the patient. So what it simply gives you, we are going to take a patient and it's his or her gender, age, total cholesterol level, high density lipid. So these are something to do with blood. I mean, the blood report, right? The lipid profile, and smoking or not, blood pressure medication taking or not, type 1 diabetics there or not, type 1 diabetic patient or not. And this is simply gives you the risk of having a heart disease from 0 to 100, right? Risk of having a heart disease from 0 to 100. But I'm not sure about this source, but anyway, this is, I will probably provide you the source of this data set. But anyway, this is a verified data set. Simply, it's like the age, gender, total cholesterol level, and the HDL, high density lipid, something to do with the blood report, and smoking or not, blood pressure medication taking or not, type 1 diabetics, yes or no, type 1 diabetics is there or not. Then finally the target will be the risk of having a heart disease, right? Okay. So now you may be wondering, here we have 7 features as I can remember, or 6 features, yes. Exactly, this has 6 features, not only one. Right? So that means, for example, if you go back here, right? That means what? If you like provide this data set into a machine learning algorithm, it's something like this: x1, x2, x3, and x6, and finally y. Now, can you think what happens now? Earlier it was quite fine, like y equal mx plus c, but what happens here now? It's still the same, right? This provides you y equal fx, but this time y is a linear relationship between all the features. A linear. This is a linear, not polynomial. It's a linear. Why I say like linear? You will see a1 x1, a2 x2, a6 x6 plus a0. Right? Why I say linear? Right? It's not going beyond degree 1. Right? You are not going to find like some values like a1 squared, a2, x2, I mean x1, x2, x1, x2, right? Or like like a3, x1, x2 squared. No, those kind of parameters, I mean those kind of coefficients are not there. Like this is a linear relationship, but you can't now plot it in a graph, right? So you don't have x-axis, but you can't plot it in a graph. But this is what happens now. So instead of giving you m and c, that means m and c is what? If you refer a, m and c equals to what? a1 and a0, right? M and c refers like m is a1, c is a0, right? So similarly here, what it gives like a1, a2, a3, a4, a5, a6, and finally a0 is the coefficient, I mean the constant, right? So when you are going to provide like multiple features into the machine learning algorithm, I mean the linear regression algorithm, it's going to provide you this amount of coefficients, right? Got it? So it's a linear relationship. This is a y is I mean the risk is a linear relationship between x1, x2, x3, x4, x5, and x6. Right? Now I will show you something here. So let us add this data set. I mean this one, right? So sorry, not this one, this one. Right? Now this is how I'm talking about again the height and weight, the weight and height example. So one feature and one label. So data will be the weight, right? So you can see data is the column number 1, target is the column number 2, right? Target is the column number 2. So one feature, one label problem. So when you apply it to the, when you split and when you apply it to the machine learning algorithm, here from sklearn.linear model linear regression. So this is how we are going to get the linear regression algorithm, right? So when you take the linear regression algorithm and when you apply it to the machine learning algorithm, right? So the machine learning algorithm simply gives you what? It gives you the train data and the train target, right? The train data and the train target, and you using that you train the model. Now you are using a linear regression model. So then what you can do, you can get the coefficient and the intercept, right? So this is the m and c. So after training the machine learning algorithm, I told you, right? So linear regression algorithm gives you the best fit line. So like what do you mean by giving a best fit line? Is giving you like what? M and C. It gives you M and C. Now, since you have one feature, it gives you only one coefficient. That means the M. That means A1 actually, A1. And constant all will there will be only one constant, so that will be A0, right? So these are those values, right? But what I want to show you now here, this actually, if you want to have a look, you can have a look how this equation came, like you can remember, right? Uh, uh, right. So it gives you how to find these parameters, and the same thing will be applied for multiple coefficients when you have multiple coefficients, right? So when you have multiple variables, I mean multiple features, what simply machine learning algorithm does, right? What the machine learning algorithm does, as I mentioned, x1, x2, x3, and x6 and y finally, this provides still a linear relationship like this, but the linear relationship will be something like this. Finally, a6 x6 plus a0, where a0 is the constant, right? Okay, so now quickly let me apply the data set. Now what I'm doing here is reading that cardio CSV data set, right? The cardio CSV data set, and I load it to the data set. I'm loading it to the data set, so the CSV file. Now we did it in the first week as well. You know, the iris flower example, we did the same thing, right? So we get the data set, and this is like split in the columns. That means what? Uh, we sorry, uh, we go up to here, right? 0, 1, 2, 3, 4, 5, 6, 7. Up to 7 is up to 6, right? So we go up to 7. That means we take the features. Yeah, we take the features 0 to 7. Now I told you in Python there's important thing, the upper limit always will be 1 less than the given value, right? So that means 0 to 7 is 0 to 6. Then we take the seventh column into the target. That means what? This one. Seventh column into the target. So first 6 rows here, and finally the target, right? So we take the data and target, then we split into the thing, and now we get the linear regression algorithm, and we train it using the train data and test data, right? The cardio data set, I'm taking it and training, test, and split, right? And get the linear regression algorithm and fit it. And now you can see when you have the coefficient, model dot coefficients, how many coefficients are there? Huh? How many coefficients are there? Right? So you have 7 coefficients, 0 to 6. That means the first one is the coefficient of the age, second one is the coefficient of the gender, this one is the cholesterol level coefficient. Likewise, for each feature we have a coefficient, right? So that's a linear relationship, right? And finally we have the constant A0 minus 13. So that's the constant, right? Understood? So then what we'll do now, you know that these are what? A1, A2, A3, A4, A5, like finally this is A7, right? And this is A0, right? So you know what, how a prediction can be given, y dash equals a1 x1 bar plus a2 x2 bar, right? Finally you can a6 x6 bar and a0, right? This is how the prediction is given finally. Understood? Now the next thing is that we can get the predictions. Now the test data, as usual, we apply the test data and we get a prediction, right? And these are the like first 10. Now this data set is a very large data set. I think there are 6,000 something. Yes, 6,000 values here, a very large data set. So 6,000 something is there. So yeah. So what happens here now, like now 6,000, we use 10% for testing here. 10% for testing in the sense like we are having only, I mean, we have something around 600 for testing, right? We have something around 600 for testing. So we can't visualize each and everyone here. So what I did was I showed here the first 10, right? The first 10 of predictions out of somewhere around 600, right? So these are the actual and these are the predicted, right? Okay, now we can get a clear idea by looking at this. So is there, I mean, can we use the accuracy as we did for other classification problems, and can we use the accuracy and measure the accuracy of a regression problem? What do you think? Yes, what do you think? Can we measure the accuracy of a regression problem? Can you remember the equation of a regression problem? I mean, can you remind the equation of the accuracy? Can you measure the, I mean, can you give me an equation for the accuracy? Yes, anyone? Can you remember? Yes, accuracy. Number of correct total number. Okay, great, thanks. So can we, I mean, would we be able to use it here? Can we use it here? Can you use it here simply? What do you think? Can we measure accuracy of a regression problem? No, right? Why? Huh? Now, the thing is, right? Okay, so let's say the predicted one is somewhere 2.6. I'm taking an example, and the actual is 2.5. So is it a correct prediction? If you take the accuracy, is it a correct prediction? If you take the accuracy, is it a correct prediction? No, right? It's wrong, right? So there will be like, this will be taken as a wrong prediction, but still the same. I mean, very, very close, but still, if you measure the accuracy, it will be 0, right? Got it, right? I mean, okay, now I like, okay, now these are also, I mean, okay, the risk of having a heart disease 30, right? Risk of having a heart disease 22 and 28, right? Now can you see, now risk of having a heart disease, these seems the same, right? I mean, very less, right? Very less heart risk level. But I mean, okay, 88 and 95, What do you think? I mean, for the heart risk level, what do you think? 88 and 94, right? 88 and 94, quite close, right? I mean, definitely this man is in a very danger, right? 88, right? 88, 95, like quite the same, right? But what will happen, like this kind of a thing for a self-driving car? Think the angle, the predicted is something like 20, but the actual is something like 28. Huh? A self-driving car, think angle 20 and 28, or 20 and 20 and 29, let's say. Right? A huge damage, right? Yes, a very sensitive thing. So now these things are like always depend on the application, right? Don't think okay, this is like these regression problems, if it is very close, I mean 22 and 28 are the same, 88 and 95 are the same. Don't think like that. I mean, if you go to self-driving car, I mean, for a stock market value prediction, okay, so stock market value is 100 or 120, quite the same, we can say, right? But a self-driving car, no, right? Understood? Got it? So depend on the application, we can't always say, but anyway, accuracy won't work in any case, right? Therefore we have another method in order, like this is some specific method that we are using in regression problems. It's called the R squared method, R squared score, right? R2 score, right? So this is what you mean by R2 score, right? So what we are going to do now, we are going to measure the errors, right? So let's say that these are yeah, so this is called like the data points, and we are going to take the error between the best fit line. So these are called the bar, I mean not bar but hat errors. Error hat 1, error hat 2, error hat 3, error hat 4, error hat 5, right? Then we are going to define another error, right? Another error. Let me use another color, probably blue color. Then we are going to draw the what? This is the X bar of this data set. Sorry, the Y bar of this data set. The Y bar of this data set. Then we define the Y errors. Sorry, the bar errors. This is the error bar 1, and this is the error 2 bar, and this is the error 3 bar, and this is the error 4 bar, and this is the error 5 bar, right? Got it? So hat errors will be like the data points and the between the data points and all the lines in the regression points, right? And the hat error will be, sorry, the bar error will be the mean value of Y and the data points. We are going to measure these errors and sum them up, right? And then what you are going to do, these two errors are applied to this kind of a equation, R2 square. R2 square will be simply 1 minus sum of hat errors divided by sum of bar errors, right? So R2 score simply gives you a idea similar to the accuracy. That means like more, I mean, when it's closer to 1, it's a good score. When it's closer to 0, when it's going away from 1, it's a bad score, right? So the meaning is similar to the sense that you are getting in R2 score is quite similar to the accuracy, So when it's closer to 1, that means it's a good model, and when it's closer to 0, it's not a good model likewise. Got it? But this is how it is, right? So if you carefully carefully look at this equation, it makes sense, right? What should happen in order to make R2 score 1? R2 score 1 means the best model. R2 to become 1, what's the requirement? What's the requirement to R? I mean, what's the requirement R2 to become 1? Yeah, exactly. So this part should become 0, right? What it means, if you go back to the earlier one, huh? What it actually means. These errors should be 0, right? That means those points should be on top of the best fit line, on top of the best fit line, right? All points should lie on the best fit line, right? Best fit line. That means the perfect, the ideal best fit line, right? That means, in other words, we can say when the points getting closer and closer to the data, I mean the best fit line, the R2 become closer and closer to 1, right? Got it? So when the data points gets closer and closer to the best fit line, R2 score become closer and closer to 1. So that means a best mode, I mean quite gospel, right? So what we can do is, this is how, like, from sklearn.metrics, import R2 score, like the accuracy, and you can measure the R2 score like this, right? So we are getting something like 77. Not best, but a good. But we have lots of method of improving this accuracy. We will talk about this in unsupervised, I mean, the coming sections, right? How to improve this R2 score, but that's it for now, right? Okay, so the practical session simply from this one will be something like this. Now we have a model which can predict, once this age, gender, total cholesterol and everything is given, there is a method where we can use to predict the heart risk level. So therefore, what we are going to do is we simply create this kind of a backend, and this will be the practical of this one. So let me run it and show you. We will do it in the next day. I will guide you step by step on this one, how to do this one. So this kind of web application we are going to write the name, the gender, right, the age, the total cholesterol level, the HDL level, the SB, these kind of things, right? And simply it provides us the risk of having a heart disease. It provides us the risk of having a heart disease, right? So this web app, now very important thing, we have integrated the machine learning model that we just trained now into a web application. So very interesting thing to do, right? So we use Flask web framework. We use the Flask web framework in order to do this, and using that we will do this implementation on next week. I mean the next day, right? Okay, good. So any questions from the sections that we have covered today? Anything that you need to clarify? Yeah. So those who have errors can wait, and others can leave. So Prabhat, you have an error. So I will allow you to share your screen. So can you please share your screen and show me the error that you are having? Yeah, Prabhat, can you show me the code?
Yes, sir, 1 minute, wait.
Sorry. Uh,
Yes, sir.
yeah, yeah, yeah. Show me the error code.
Sir, actually, sir, 1 minute, sir.
Yes, yes, it's fine.
Sir, actually, yeah, uh,
Yeah, what's the issue you are having?
actually, that algorithm we can train that cannot predict our answer correctly.
Okay, so can you please open your code and
Just,
code and show me?
yes, sir.
The thing is
So
now,
that's good.
yeah, Prabhat, you have shared another screen. So can you go to share again? Now it's fine. Okay, so now I can see your one. Can you allow the request for the remote control?
Yes, sir.
Okay. So now, what was your issue? It's not giving you the answer, is it?
Yes, sir.
You mean the window is not shown, is the case?
No, no, sir. Only when number was guesses, that was not correctly predicted.
The others are not getting predict correctly, right?
Yes, sir.
Okay.
Yes, sir. So that I cannot sort only that was printed, but some cases that cannot give us a correct answer.
Okay. Now,
Yes, sir.
um, you have, it's giving two, right? Isn't it?
No, no, sir. Only some cases, and but other cases not given answer.
You mean like this, right?
Yes, sir.
Yeah, Prabhat, the thing is now this is not a perfect method, right? So what we have like I mean, what we have to do is you have like
Yes, sir.
write it perfectly. Now, what we did was uh, yeah. Now there are lots of issues here, right? The thing is, uh, now the data set that we used, right? So they are handwritten digits,
Yes,
right? They are handwritten digits.
yes,
That
sir.
means like they are not now. This is a digitally I mean created image. Now what we are writing here is digitally created. So those are handwritten digits. And now you can see the only color in this image is black and white, right? Only black and white, right? But can you go to the
Yes, sir.
training code that we did?
Yeah.
The training code that we did.
Yes, sir. 1 minute, sir.
Okay.
That was uh, which GUI code?
Yeah, I think that one.
So that was GUI code and that was
Yeah, that one.
training key and date and digit. Yes,
Yes,
sir.
that one. So can you go to the where that we just show? I mean, we show a image We didn't show. Ah, yeah, here. So can you see now here? Uh, yeah. So can you see now? Like these are having black gray pixel values as well, right?
Yes, sir.
Ah, I forgot one major thing here. Uh, Sorry about that. I don't know how these predictions are given correctly. Yeah, yeah. I made a huge mistake. I mean, I forgot to do that. Let me quickly have. I will share the screen again, and I will correct it in my one. Right.
Okay.
So I forget actually one thing to do. Let me go back here. Um, yeah. So what I forgot to do, very silly mistake actually. Now. Hmm, yeah. So I think this is what we did last time. And let me run my one and see whether I'm getting
Yes,
it.
sir. Sir, that was the code which was given with us.
Yeah, I think the issue is this now. I actually forgot to do this.
Yes, sir.
Uh, so here, can you see when you, now this is the image, right? One image. So you can see that the values are, like I
Yes,
told
sir.
you, usually in images, the value range is 0 to 255, right? 0 to 255. But the
Yes,
thing
sir.
here is this in the digits data set available in scikit-learn, they have like compressed the image. Now it's in not a 8-bit form, it is in not 8-bit, but it's in 4-bit form, right? So that means like the
Yes,
values
sir.
are in range from 0 to 16, right? Not
Yeah.
0 to 255.
Yes, sir.
It's not 8-bit, it's 4-bit. So that means
Yes.
0 to 16, right? So that means whatever the
Yes,
images
sir.
that we have trained now, see, can you see the white color here? White color is
Yes,
represented
sir.
by
Yes, yes, sir.
16, right? Understood? That's not
Yeah.
255. Got it? So therefore, now, but what we
Yes,
have
sir.
here in our code is that it is simply like 0 to 255, right?
Yes, sir. Yes, sir.
Now, whatever the image that we are getting are 0 to 255. Now, let me print you and show you this image array, right? So these images are, so let me get a prediction. Can you see? Now, these are between 0 to 255. See? But
Yes, sir.
the images that we used are between 0 to 16, right? So that means the range is different. So this is a huge effect on our thing. So what we can do is simply we can get rid of that by doing this. So now the range is in between 0 to 255. What we can do is we can convert it to 0 to 16, 0 to 15, actually 0 to 15. So how we are going to do that?
Yes, sir.
You can simply divide it by 255. So now what happens? All the pixel values will be divided by 255, right? Individually, the
Yes, sir.
pixel values will be divided by 255. That means this converts all the pixel values to in between what? Any idea? okay, let's say the minimum value is 0 and the maximum value here is 255. So 0 to 1 divided by 255 gives you 0.
Yes.
So this one gives you what?
0.
This one, the second one.
1.
So
1.
yeah, so this simply what? This simply converts the image, the pixel values which has 0 to 255. Now this convert into 0 to 1, right? So now what I'll do, I'll simply multiply it
Yes,
by,
sir.
yeah. Now this convert it between 0 to 15, 0 to 15, right? Right, so the conversion is now done.
Yes, sir.
Now let us see whether it's giving you correct values. Now can you see the image is now converted into this kind of
Yes, sir.
right? Okay, I actually forgot to do this. I think now the results are better, right? Check it now, doing that one. So this is the modification I just did,
Yes, sir.
this line.
Okay.
Okay, I
Sir.
think that's the issue. Okay, try to do that and
Okay.
see the output. Okay, any other questions from you all?
Okay.
So please, others also like uh, try to do this, and can you inform others as well to do this modification, the other participants? If you have some access to your group and or whatever the group you are in, you can, right? Okay, so any other issues you may have? Yeah, Ravi Kumar, can you share your screen and show me the error you are having?
Hello.
Yes, Ravi.
Yes, I am getting the error in today's application we made.
Okay. Yeah, let's see.
Okay. 3 and this one testing as well. Okay.
Right.
I will run this. It gives me this correct prediction, but it give me this error. And kernel dies.
Okay. So have you included some new photos as well? No, the same
No,
photo.
sir. No, sir. You can see my directory too.
Okay.
This test data.
Test data.
This.
Right. I think that file, if it's having some kind of extension, the first file,
Which one, sir?
the first file in the test data.
Test data.
Yeah.
What we have to do, sir?
Yeah.
I'm
Go to
not
the
getting your voice
test data
clearly,
folder.
sir.
The test data folder.
Test data folder.
Yeah. Can you open the first file?
First.
Yeah.
Yes, sir.
That is not supported. So can you just delete it? I'm not sure what's the issue, but anyway, delete it.
Delete. Okay,
Yeah,
sir.
just delete it.
Hmm.
Now
I
try
delete it.
run it. Now it's fine, right?
Yes, yes.
Yeah, the thing is,
But it not giving me files, sir.
yeah, I think the issue was with Ravi. Now that image was corrupted. I don't know what's the reason, but anyway, it's corrupted, not supported. That's why.
Sir, but I am getting the gray image. Now I am getting correct.
Yeah.
Thank you, sir.
Okay, okay, Ravi. Thanks.
Thank you, sir.
Okay, right. Thanks. Now, any other issues from you all? Everything is fine. Yes, you can share your screen. Okay, then. So thank you very much, and we will meet on next day. Have a good night, everyone.